take it away, Scott.
Perfect. Excellent. Thank you very much for the introduction and for having me here today. So what I would like to do today is share with you all some recent progress in bringing amplitude techniques from particle physics into cosmology, and in particular, how we can use recent successes on the amplitude side, like unitarity and positivity bounds, to constrain the cosmological correlations that are imprinted in the CMB at the end of inflation. So it's hard for me to overstate just how successful particle physics has been in recent years in developing a truly staggering range of sophisticated techniques which allow us to compute scattering amplitudes with an unprecedented efficiency and precision. But these techniques also provide a new array of tools with which we can constrain field theories. So in particular, of this mosaic of different techniques, today I'll be focused on these two on the right-hand side, unitarity and positivity, because we now have a very good understanding of how to check, given some scattering amplitude, whether it was produced by unitary time evolution, i.e. whether the underlying physics was consistent with just basic quantum mechanics. We also know, similarly, how to check whether an amplitude is consistent with the underlying physics being causal and local. Okay, so to really hammer that point home, here's a plot taken from a paper last year in which these authors asked a computer to scan over all possible values of 3 parameters that appear in a Lagrangian, and asked the computer to color in which parameter values are actually consistent with unitarity, causality, and locality. Okay, and the result is fantastic. It's this really narrow potato chip shape, which is really showing us that when we just write down some field theory Lagrangian, although it superficially looks valid for any value of its parameters, there are secretly large regions of parameter space which are just unphysical. They're not consistent with one of these basic physical principles. Now, on the other hand, in the cosmology community, we are now measuring primordial signals from the early universe with an unprecedented precision. But there is a problem. So this is a plot taken from Planck's most recent constraints on inflation. And the thing that I want you to take away from this picture is that while the gray and red and blue bananas here are the observational constraints, this much longer list of colored rods and lines are just some of the available models that we have to describe the early universe. So each of these different models has parameters that you can tune, and that's why these colored regions kind of sweep out bands in the plot. And you can see that almost all of these models have some values of their parameters which are broadly consistent with the data. So in some sense, we've just been far too imaginative when it comes to building these models of the early universe. There's just no way to decide between this laundry list of theories with the data that we have. So really what we need is a way of being more selective, okay? Some way of going through this list with a filter to weed out the models or the parameter values which are secretly inconsistent or unphysical. So that's been the goal of much of my recent research, okay, to try and take these new field theory constraints developed in particle physics by the amplitude community and try and apply them to this list of cosmological field theories so that we can deselect the models or parameters which are secretly inconsistent with causality or quantum mechanics and really tidy up this picture to get a better understanding of the fundamental laws that describe our universe. So hopefully you're thinking, great, that's a great idea. Let's get started. Let's do that. But unfortunately, there's an obstacle that we have to overcome. And that is the fact that, for good reason, in the amplitude community, people always assume Lorentz invariance. Okay? They're interested in collider physics, scattering particles on an approximately Minkowski spacetime background. And for us in cosmology, that's just not good enough. Okay? We're interested in some expanding spacetime background, some FLRW kind of metric. And because this background depends explicitly on time, it really breaks a lot of that symmetry. It breaks time translations and it breaks boosts. So really today, what I want to tell you about is how to overcome this obstacle, right? How can we take those amplitude constraints and adapt them to situations where Lorentz invariance is broken? And ultimately, that will give us a new set of tools that we can use to better understand the space of cosmological field theory. So let me give you a simple example of what I mean by a model that breaks time translations and boosts. So to illustrate the bounds I'm going to develop today, I'm going to focus on this theory here. It's called the effective field theory of inflation. It's been around since 2008, and it was constructed with this idea of writing down the most general description of scalar fluctuations produced during inflation. Okay, scalar fluctuations produced on an expanding FLRW background can be described by a Lagrangian of this form. And okay, there's many terms, but it helps phenomenologically to kind of group them together. The first two terms are quadratic in this scalar field pi. And so really what they're controlling is the power spectrum. How correlated are pairs of points in the CMB? Then you go on to the next order. These ones are cubic in the scalar field. And that's really controlling the bispectrum. How correlated are 3 points on the sky? And then you have quartic, 4 powers of the scalar field interactions. They're controlling how correlated are 4 points in the CMB, and so on. But now if I were to put on my particle physics hat, right, I would say that this is just a Lagrangian, and I can interpret each of these interactions as some Feynman rule, okay, as some rule that lets me draw Feynman diagrams and associate to each cubic or quartic vertex some factor of the interaction coefficients. Good. So for example, this one at the very end here, it has 4 derivatives. So in momentum space, I'd have some very simple Feynman rule that tells me that every time I see this kind of vertex, I should replace it with 4 powers of the momenta contracted together in some nice way. And that's the kind of Feynman rule that we know how to deal with in particle physics, and we have good amplitude constraints for. The problem is really all of these other guys, okay, these interactions that depend on explicit time derivatives of the scalar field, like pi dots. Because in momentum space, they just depend on some energy. And the energy itself is not a Lorentz invariant quantity. Okay, these other interactions are not invariant under boosts because they correspond to amplitudes that depend on the absolute value of the energy that some particle has, and not on a Lorentz invariant contraction like p mu, p mu. Now, the second big difference with particle physics is that actually each of these interaction coefficients, the alpha 1, alpha 2, etc., in general, they can just be explicit functions of time. Okay, so that's the other big departure from, say, doing standard model scattering, where all of the parameters in Lagrangian would just be constants. Good. So these are the kinds of obstacles that we need to overcome if we want to take the amplitude technology and apply it to cosmology. Now, that's actually a very difficult problem, right? Trying to adapt amplitude techniques for situations like this. So today I want to focus on a baby step in the right direction. And that's to tell you about what happens when you break boosts and not time translations. And the reason that I can do this, that I can separate out the breaking of boosts from the breaking of time translations, is that I can do the following thought experiment. I can imagine on my expanding space-time background, preparing a pair of these scalar fluctuations, and then having them interact with each other and come out again in a box, right, over time and spatial scales that are much smaller than the curvature of the expanding space-time background. Okay, so the frequency of everything I'm going to be scattering can be larger than the Hubble rate. And what that means is I can treat these interaction coefficients as effectively constants. So in this idealized thought experiment, right, my little box with my scattering process, I only have to worry about the fact that these interactions are breaking boosts, but I can treat time translations as some approximate symmetry that the system still has. So the first things I want to tell you about today are how to adapt amplitude techniques to systems that break boosts. Fantastic. So what I've told you so far is that these new amplitude techniques give us great ways of constraining which field theories are secretly consistent with unitarity and causality, and cosmology is really in need of these kinds of constraints. However, to really apply them properly, we need to go beyond the Lorentz invariance that's usually assumed. And in particular, today I'm going to tell you about two kind of recent advances in this direction. The first is how you take unitarity bounds and apply them to systems without boosts. And the second is how to take these grander positivity bounds and apply them to systems without boosts. So before I get started, let me stress that, of course, nobody works in a vacuum. And although I'm going to be focused mostly on these two papers that I wrote with a student in Cambridge, Tanguy Graal, this is really part of a community-wide effort to try and bootstrap as much information as possible about cosmological correlators using only these fundamental properties like unitarity and causality. And there's a lot of people that are working in this direction, and I don't want to do any of them a disservice by focusing only on my two papers. That's why I've listed their names here. Great. So before I get started with unitarity, are there any questions about the overall motivation? Excellent, great. So we're all on the same page. So let me start by telling you what unitarity means in particle physics. And if I had to explain it to my gran, I would say it's very simply that whatever goes in to my scattering experiment has to come back out again. Okay, so mathematically, the way that's implemented is if we start with some state in the past that has some particles in it, and we let that evolve to some future state, that time evolution is implemented by some operator, S hat. And unitarity is the idea that if I start with some normalized probability distribution in the past, in order for my future probability distribution to remain normalized, then this S hat had better be a unitary operator. S hat dagger S should be 1. Now, this as an equation is really an operator valued thing because of these hats. And in practice, what we work with are these transition amplitudes, which really, when I square this thing, it tells me how likely am I to have transitioned from the state in the past to the state in the future. And this condition in the box becomes a much simpler condition on the amplitudes, namely that each scattering amplitude has a modulus that's bounded from above. And that kind of makes sense if you buy this probability picture I was describing. If all the probabilities are to remain, summing to 1, then each individual probability had better be less than 1. So these kinds of constraints, right, that each scattering amplitude in your theory should be bounded from above, they've been incredibly successful over the years in particle physics, right? So two, perhaps, of the most famous examples are long before we built the LHC, we knew about W and Z bosons. And in a theory that has only W and Z, but not the Higgs, then you violate these bounds. And exactly where you violate the bounds tells you useful information about where the Higgs needs to live. The other way to use these bounds when you actually don't have the experimental data is just to demand self-consistency of the theory. So an interesting example of this is the low energy theory that describes pions, the low energy theory of QCD. And there you can get interesting constraints on how pions should be interacting with each other just from the requirement that the theory makes sense, i.e. it's unitary, at energies close to the pion masses. So really what we would like is some analogous bound that we can apply in cosmology where boosts are broken so that we can enjoy some similar successes. So before I tell you in equations exactly what these bounds are and what it is we've achieved, let me just show you a cartoon of what you might hope this is buying you. So when we write down this simple effective field theory, okay, that it depends on just a single scalar field pi, the idea that we have in the back of our minds is that this is just some low energy description, and that ultimately at some energy scale, say big M, there's going to be a new field or a new kind of particle that becomes important that can start to contribute to these scattering processes. And so my effective theory is going to break down because my effective theory just doesn't contain any information about these guys. Great. Now, where does the theory break down? Well, in terms of this Lorentz invariant energy, S, right, that appears in the Feynman propagator, you would expect that the low energy amplitudes start to become one and violate unitarity when this energy really coincides with the mass of the new physics that's completing this theory at high energies. So the idea in particle physics is that by studying how this EFT breaks down, where these amplitudes start to violate unitarity, you're really uncovering some information about the new physics that lies beyond your effective theory. In this case, you're learning something about the mass that it would have to have. So in inflation, right, if we want to apply the same logic, the twist is that there's now a new scale in the game, okay, which is the scale at which Lorentz symmetry gets broken. Okay, we call that scale f pi. The idea is that when you're at low energies, then this expanding spacetime background breaks your Lorentz invariance. But if I were to go to incredibly small scales, right, if I start talking about LHC physics, clearly I don't need to worry about, the fact that the universe is slightly expanding. So I can treat everything as Lorentz invariant. So there's a scale at which I can start to just treat everything as Lorentz invariant. And now, if I think about how new heavy physics can UV complete this theory, I actually have two options now. One option is that the new physics appears at energies above the symmetry restoration scale. And then it appears very much like it does in the particle physics case. Okay, there's just some dispersion relation, some equation of motion of this heavy physics, which depends on this Lorentz invariant omega squared minus p squared. And that tells me where the theory should break down. But there's a new possibility, which is that the new physics becomes important before Lorentz invariance gets restored. And in particular, in that case, this new physics can have some equation of motion, which isn't Lorentz invariant. It can have some speed, the speed of new physics, c nu, that isn't 1, and it can have some mass. And so really we expect some picture like this, where this effective description is going to break down at different places in energy and in momentum. Okay, another way to say that is that this theory has different cutoffs, different resolving power in time and in space. And that kind of makes sense. We've broken boosts, so there's no reason why you would expect the temporal and the spatial cutoffs to be the same. And in fact, here's a very simple example where the new physics is characterized by just a single mass and a single speed. And in general, you might expect that if the new physics is sufficiently wacky, it might lead to a breakdown of the EFT that is just some curve in the momentum energy plane. So the idea here is that by studying how the effective theory breaks down, really what we're doing is drawing this red line here, and we're learning not just about the mass of the new physics that would have to complete this theory at high energies, but we're also learning something interesting about its dispersion relation. We're learning something interesting about how it propagates, things like its speed and higher order corrections to its equations of motion. Good. So now I'm going to tell you in equations how we actually draw these lines. Okay, that's really what we've achieved. By studying unitarity in a boost breaking context, we can now draw these curves and tell when the EFT breaks down in energy and in momentum. So the central object that we're going to be using is this 2-to-2 scattering amplitude. So I'm going to draw it in pictures like this. I have two particles coming in with momenta P1 and P2, and then they go out again with momenta P3 and P4. And mathematically, what this diagram means is some matrix element, some ket, and then this S hat operator that implements the time translations, and then some bra. So it's just some complex number. But the nice thing about this object is that my unitarity condition, right, which was that this S hat operator is unitary, it has a very nice diagrammatic representation in terms of these amplitudes. I can actually show that from the condition that S hat is unitary, this requires that this amplitude, this matrix element, has an imaginary part, which we draw as this dashed line here, as an imaginary part given by summing over all the ways that my two particles can become n times all the ways that my n particles can go back to being 2. So mathematically, this is like resolving the identity. I'm sort of inserting some complete set of n particle states. Cool. So this is really equivalent, these two things. However, this bound here, in terms of these amplitudes, is in practice not so useful, because to really implement this, I would need to know the scattering amplitude for any 2 to n process, okay? For any n goes up to infinity, so I have an infinite number of things I would need to compute. So what we can do instead is the following trick. We can notice that every term in this sum really looks like some complex number times its complex conjugate, right? So they're all positive things. So what I can do is I can split this sum up into the term where n is 2 plus the term where n is literally anything else. And I can throw away all the n not equal to 2 terms and replace the equality with an inequality, okay? Because I'm throwing away strictly positive things. And now we're in business, because now I have a bound which relates the 2 to 2 amplitude to just a product of 2 to 2 amplitudes. So if I can compute this diagram for you, then I can check whether it came from some unitary dynamics by checking whether it satisfies this bound. Okay. Now the sum over all n has really just become an integral over the possible momenta that these internal lines could have. Good. But now this isn't quite what I promised you. It's not quite the bound that the imaginary part is bigger than its mod square. In particular, it has this integral that you have to do over all the momenta. And if I decorate this diagram more precisely, you'll notice that this A and this A star actually depend on different kinematic arguments. One of them has a P1 and a P2. The other one depends on P3 and P4. So if I actually want to take this bound and turn it into what I promised you, that each of the amplitudes is somehow bounded from above, then there's 2 conventional steps that we need to take. What I want to do now is tell you what those 2 steps are, so that you can see why they don't work in cosmology. So the first step is to try and use all of the symmetry that we have. Okay, if we're doing this in particle physics, then we have 3 boosts, Lorentz invariants, and we also have 3 rotations. So the first order of business is to try and implement those symmetries to simplify this bound and simplify this integral. So the way we do that is we use our boosts to basically go to an inertial frame in which the center of mass isn't moving. We go to a frame in which the momentum of particle 1 plus the momentum of particle 2 vanishes. Now, if you like, you can think of this as fixing particle 2 in terms of particle 1 and fixing momentum of particle 4 in terms of the momentum of particle 3. So that rather than this amplitude depending on all 4 of the momenta, it really only depends on P1 and P3. So that's the first thing. Then the next part of this step is to use your rotations to argue that if you have a function of only 2 vectors, P1 and P3, then the only thing that can really matter is the angle between them, their dot product and their norm. So what these symmetries buy you is that really this amplitude you can think of as being a function of only 2 things, just one energy, the total ingoing energy, and one angle, namely the angle between P1 and P3. Great. Now that makes your life a lot easier, because the second step is then to say that I can take this function, right, which depends on one energy and one angle, and I can do what we call a partial wave expansion. But if you like, this is an angular Fourier transform, which is just replacing this one angle with an angular momentum. And the nice thing about that is that angular momenta are conserved because of rotation invariance. So when I write my amplitude, instead of being a function of s and theta, as this little a of L and S, now it's a function of one angular momentum and one energy. And that's really achieved what I set out to do, because now this bound here, which involved an integral over all of the possible linear momenta that these particles could have, that integral vanishes. And now you have a very simple bound, which just says that the imaginary part of this amplitude at fixed angular momentum and fixed energy is bounded by the mod of this amplitude at the same angular momentum and the same energy. Okay, the only way that can happen for a complex number to have an imaginary part greater than its modulus is if its modulus is less than 1. Okay. So before, when I said that, oh, these amplitudes have to be less than 1, strictly speaking, what I meant is that if you write the amplitude in terms of one angular momentum and one energy, then those are the things that are bounded. So to give you an example of how that's used in practice, right, if we consider turning on just a very simple interaction in the Lagrangian, okay, something like this Lorentz invariant d pi to the 4, on dimensional grounds, it has to come with some UV mass scale, this big M to the 4 downstairs. So if I use that interaction, compute the scattering amplitude, I'll find that the first of these partial wave amplitudes, the one with L equal to 0, is just given by some numerical coefficient, which this formalism is fixing for me, times the ratio of S over M. Okay. So when does this thing exceed 1? When does unitarity break? Well, it breaks if the energies get higher than some maximum, which is really M squared times this numerical factor. So that's telling me now about the new physics which would have to become important to UV complete this theory. Great. So that's how it's usually done. Now, in cosmology, right, if we're looking at systems that break boosts, then we have to revisit this first step here, okay, where we used our freedom to just pick an inertial frame to set the center of mass to be stationary. That's no longer an option. And one way to see why it's no longer an option is to think about how we've fixed our coordinates. Okay, we've sort of already fixed our coordinates so that the background expansion is isotropic. Okay, if you like, we're working in a frame where the background metric is some simple FLRW thing. And so now on that space-time, right, in this frame, if I scatter some particles, okay, their center of mass is just going to be moving with some momentum. And I'm no longer free to just do a boost to bring this thing to rest. Because if I try and bring the center of mass to rest, what it's going to do is change my coordinates. It's going to make this expansion anisotropic now, right? So really the best I can do is just allow for the center of mass to be moving however it wants to move. I just have to redo the steps that I described before, but now I'm not allowed to use my boosts to fix the center of mass motion to be 0. I just have to let it be some value. But I still have my 3 rotations. And so what I can do is I can use 2 of those rotations to fix the direction of the center of mass motion. For instance, I can align my z-axis, say, along the center of mass momentum. And the reason that's convenient is that then I can parameterize all my other momenta, say the momenta of particle 1. I can write that in terms of just 2 angles on the sphere, namely the angles that it makes with respect to the z-axis, i.e. the center of mass motion, and then some arbitrary x-axis I'm free to choose. So what that means is the amplitude goes from being a function of just one energy and one angle. Now each of these ingoing and outgoing states, really I should write them as a function of one energy, one momentum, the center of mass momentum, and now 2 angles on a sphere. And what that means is the previous partial wave expansion that we did, this angular Fourier transform from angles to angular momenta, that needs to be updated as well. And the way that gets updated is it becomes what we call a spherical wave expansion. Okay, now you go from transforming an angle on a circle to transforming 2 angles on a sphere. Okay, and that's exactly what we all study when we do quantum mechanics as undergraduates. The angular momenta numbers that you need are some L, which is really the eigenvalue of L squared, the total angular momentum, and then some magnetic quantum number, the little m, which is the eigenvalue of Lz, the angular momentum in the z direction. Perfect. So what that achieves is that now this unitarity bound, right, which involved an integral over the momenta of the internal states, that integral now just becomes a sum over the angular momentum that these internal states could have, and it's constrained by that one remaining rotation that we had about the z-axis, which says that the Lz quantum numbers have to be the same. Good. So this is the exact analog of what we've seen in the particle physics case, right? Because in the particle physics case, we saw that the mod of each of these partial waves had to be bounded by 1. Now here we've broken boosts, and what that has led to is each of these partial waves, they're really now spherical waves. They depend on not just one angular momentum, but on 2. So it's like these amplitudes have 2 indices, right? They're more like matrices than just complex numbers. And so what unitarity requires is that these spherical wave amplitudes, they're less than 1 as matrices, right? If you contract this matrix with a vector on one side and a vector on the other, then it has to be less than what the identity matrix would give you. Perfect. But that now lets us do conceptually the same thing, right? By choosing different values of these angular momenta, picking different values of the vectors that I use in this bound, what I'm getting is a way of telling when the EFT breaks down in energy and in momentum. Okay, so let me show you a simple example, right, of how this machinery can really give you cutoffs in time and in space. Right, so I'm going to start with this very simple example where I just have one interaction. Now it's a Lorentz boost breaking interaction. It's pi dot to the 4. Okay, so the amplitude is very simple in terms of the momenta. There's just a single Feynman diagram, right, that looks like this. And these 4 dots, these 4 time derivatives, become just a product of the 4 energies that the particles have. Okay. And now what I should do is this angular Fourier transform, right, to replace these ingoing and outgoing momenta with an ingoing and outgoing angular momentum. Right? And then this object here, I can check when does it exceed 1? When is it bigger than the identity matrix? And what that lets me do is carve up this energy momentum plane into these 2 regions. Okay, there's a region where the energies and the momenta are sufficiently small that these amplitudes are smaller than 1, so you're unitary. But then if the energies get too large or the momenta get too large, then you lose unitarity and you require some new physics to become important. Good. Fantastic. So what's important here is that this machinery is really fixing for you these numerical coefficients. Okay, this is actually a precise curve that I've drawn here, and it isn't just dimensionally the case that the energy where the theory breaks is sort of roughly m squared. These bounds are really telling you that there's some precise numerical factor at which you expect the new physics to appear. Good. So now that this machinery is up and running, what we can do is apply it to the EFT of inflation, okay, that I showed you in the motivation. Okay, we can take this theory that had these quadratic terms, these cubic interactions, these quartic interactions. Okay, phenomenologically, they're really controlling correlations we see in the CMB. And we can ask, when does this theory start to lose unitarity and require new physics for UV completion? So we go through the same steps. Now computing the 2-to-2 amplitude is a little more complicated because you have not just one quartic interaction, but now you have 3 of them. And also these cubic interactions give you Feynman diagrams where you exchange some internal line. But you can compute all these diagrams, and then you can do this angular Fourier transform, okay, to write this angular momentum space quantity. And then use this unitarity bound, which tells you that these angular momentum amplitudes have to be bounded from above. And what we were able to show is that this requires new physics to become important at an energy scale, fixed in terms of the symmetry breaking scale and CS, the speed of these scalar fluctuations. But also that there's a spatial cutoff to this theory, which is also fixed by the symmetry breaking scale and the size of alpha 1, the size of the parameter that controls the bispectrum. So there's 2 really nice things about this result. The first is that they are numerically precise, okay, that really this is 2 pi over 15 and 30 pi, right? So you can now compare these bounds to data because you actually know exactly where you expect the theory to break down. The second nice thing about these bounds is that when you compute this amplitude, right, it depends on this beta 1 parameter. And that's a bit of a pain because observationally speaking, we have much, much better constraints on the power spectrum and to a lesser extent on the bispectrum than we do on the trispectrum. Okay, this 4-point correlation function is very hard to measure. And so if you're getting some theoretical constraint that involves beta 1, it's of limited phenomenological use because really that beta 1 could be anything from 10 to the -8 to 10 to the +8. There's a huge range that is allowed for this value. So what we were able to do is by combining different unitarity bounds for different values of the angular momenta, we were able to remove the dependence on beta 1. Okay, so these bounds now depend only on alpha 1 and CS. And what that means is we can take the constraints from Planck on the bispectrum, on the equilateral and orthogonal shapes of non-Gaussianity, which give these 1, 2, and 3 sigma constraints on alpha 1 and CS. And we can ask, when is this consistent with unitarity for our subhorizon scale process? Okay, so we're imagining scattering these scalar fluctuations in our subhorizon box, so we only worry about the breaking of boosts. And then we find, as a result of doing this thought experiment, that this theory has a spatial cutoff, which only resolves the subhorizon scattering in this white window. And if you make alpha 1 too large or CS too small, then what happens is you're losing unitarity. Unitarity is just breaking down in this effective description. And then you only really have two options. Either there has to be some new physics beyond this single field inflation description, or you're relying on some non-perturbative resummation of all the pi loops to somehow restore unitarity, because here we just computed these tree level diagrams. So it could be the case that you need to non-perturbatively resum all the loops. But either way, it's incredibly useful to have this window, right? To know where you can actually trust this theory on subhorizon scales. And in particular, this line here cuts through the data. So in future, as these contours improve, it'll be really interesting to see whether you kind of end up lying on the unitary side or the non-unitary side. And that's really pointing you towards whether you need new physics on subhorizon scales or not. Fantastic. So that was the story with unitarity. So the second thing I wanted to tell you about is positivity bounds. Now, again, let me start by telling you what positivity bounds mean in particle physics. And the idea there is that at very high energies in the deep UV, there's some complicated fundamental description of nature, right, that potentially contains lots of new degrees of freedom interacting in complicated ways. But if we zoom out and we focus just on very large scale, low energy IR phenomenology, we can describe what's going on with a much simpler effective theory parameterized by a small number of constant parameters. Okay, and one way to imagine this in the context of a scattering amplitude is that if you knew the fundamental description of nature, right, you could compute this scattering amplitude at arbitrarily high energies. It would involve lots of complicated diagrams because there'd be lots of UV physics that could mediate these interactions. But if you zoom out and you just look at very low energies, S, then you can essentially Taylor expand this object. Okay? And you can just write it as a series in powers of S, where each of these Taylor coefficients are just some constants, which are really parameterizing your low energy phenomenology. So the idea behind positivity bounds is to say that even in situations where we don't really know what this detailed physics should be in the UV, if it has the following three properties, okay, if it's unitary, so the probabilities are consistent, like I mentioned before, if it's causal, so signals propagate at some finite speed, and if it's local, so interactions are approximately point-like, right, then these three just very basic properties are enough to constrain the parameters that appear in this low energy expansion. So the original, and perhaps the most famous one, is that this coefficient here of S squared has to be strictly positive. So these bounds are really some connection between this IR phenomenology that you could go out and measure and the underlying fundamental theory, principles of this underlying UV physics. In particular, if you measured this coefficient of S squared and you found it was negative, that's telling you that there's just no unitary, causal, and local way to UV complete this theory at all energies. Okay, so that's a really big deal.
Scott, can I just interrupt briefly to ask you to elaborate on that a bit more? Maybe it's really obvious, but why C2 has to be greater than 0?
Yeah, excellent. That's a great question. So before I get into how we do this in cosmology, I'm going to give you the particle physics redux, the kind of summary of how in equations you go from these properties like unitarity and causality to some bound on C2. Yeah, great. So that's a good question, and I will give some heuristic justification for that in a moment. Here, this is more a cartoon to help orient us into what exactly we hope to achieve in the second part of the talk, because what I really hope to achieve is that in particle physics, these bounds are basically identifying some region in parameter space, which could have come from a unitary, causal, and local UV completion. So when we do this for inflation, when we do this for cosmology, really what these bounds are going to be telling us, okay, the bounds which I'll derive now, are that whatever UV high energy physics was going on during inflation, okay, and mediating interactions between these scalar fluctuations, even if we don't know details about how many degrees of freedom are there, how they're interacting, what symmetries they have, as long as they are just unitary and causal and local, so very, very basic features, that's enough to put constraints on the shapes of non-Gaussianity that you would expect to see in the CMB at late times. Okay. Good, so then we get these bounds on the CMB shapes, and if they were violated by data, it's telling you something really powerful about the underlying mechanism behind inflation, namely that it just couldn't be unitary, causal, or local. Perfect. Now to answer Tessa's question, let me give you a kind of quick motivation for why causality, right? When we mix causality into the game, we suddenly get this connection between what's going on at very high energies and the phenomenology on very low energies. And so the way I want to do this, in the interest of time, is to kind of explain how this would work for a very simple one-to-one scattering process, where one particle goes in, self-interacts, and come out again. And then I'm just going to say the words by analogy and tell you what the result is for two-to-two scattering. Okay. But let's go through the one-to-one case in steps, so you can see really what causality is buying for you at the level of scattering amplitudes. Now, we're familiar with the idea that you can represent amplitudes in different ways, in different bases. So for instance, there's a position space representation of this process, where I do a Fourier transform from momentum to position, and now it's like a correlator of two fields at positions x and y. But if you think about it, this Fourier transform is it's kind of a weird thing from the point of view of causality, because really it's telling me I should integrate over all four momenta. I should integrate over momenta that are future pointing, past pointing, space-like, time-like. This integral doesn't really know anything about the light cone or the causal structure of my space-time. So really what causality buys you at the level of amplitudes is causality guarantees that there is another representation of the amplitude, okay, this purple A twiddle, which requires integrating over only causal momenta, integrating over only P twiddle, which are future pointing, that's what this step function means, and inside the light cone, so that's what this step function means. Good. Now I can inverse Fourier transform both sides of this equation and write what is the momentum space amplitude in terms of this fancy causal representation. And I find this equation here, this is known as a dispersion relation, and they were all the rage in the 50s and 60s. And what it's telling me is that I can express my amplitude potentially at very low energies. Okay, I can imagine making this P very small, and I can write it as an integral up to arbitrarily high energies, right, up to arbitrarily large p twiddle of this causal a twiddle. So these causal dispersion relations are really some rule that tells me how I can extract from the UV theory something about the IR and vice versa. Now, the second important thing for us, which connects to the first half of the talk, is that I can also invert this equality, and I can ask what is the causal a twiddle, what is this new representation in terms of the old momentum space representation. And I find that this a twiddle is nothing more than the imaginary part of the amplitude. So actually, diagrammatically, I don't need a new purple blob. I can actually just write the usual blobs, but with this vertical dotted line to mean the imaginary part. Fantastic. So that's what causality really tells you, that if you know the imaginary part of the amplitude at arbitrarily high energies, then you can do this integral and reconstruct the low energy amplitude. Perfect. Now, when you go to 2-to-2 scattering, then the problem is a bit more involved, just kinematically speaking. Okay, now there is not just one momentum, but now there are 4 momenta, the 2 ingoing and the 2 outgoing particles. But somehow the logic is the same. The idea is that causality really guarantees that there's another way to represent this momentum space amplitude as an integral over only momenta that lie inside some causal light cone. Okay? But in particular, the big difference is that now there are 2 different contributions, right? Because either the sum P1 and P2 can lie inside a future pointing light cone, and that really corresponds to the physical process that you start in a state with particles 1 and 2, and then they evolve in time and you end in a state with particles 3 and 4. But there's another possible causal way that this process could have happened, and that's that if particle 1 plus particle 4, if those momenta lie inside a future pointing light cone, that corresponds to the process that you started in a state with particle 1 and 4, and then they evolved in time and you ended in a state with particles 2 and 3. Good. Great. So usually people write this using these Mandelstam variables, right, which makes this very simple. When are P1 and P2 future pointing inside a light cone? Well, that's when S is positive. And when P1 plus P4 future pointing inside a light cone, that's when U is positive. So we get the analogous dispersion relation for 2-to-2 scattering, which is the same idea, saying that this low energy amplitude, okay, I can think of each of these momenta as being very small, it's equal to an integral over the imaginary part of the amplitude, but up to arbitrarily high S and arbitrarily high U. Okay, so this is really connecting the UV of my theory, at least the imaginary part of the amplitude in the UV, with what I would measure in the IR. Fantastic. But now that's not quite what I promised you, right? That's what causality tells you about the amplitude. But really what I promised was that somehow if I expanded my EFT amplitude and powers of the energy, that each of these coefficients were going to magically be positive. So now again, let me just sketch the 2 steps that people do to convert this causal relation into these positivity bounds, so that you can see why they will not work for cosmology and what we'll have to do to fix them. So again, the first step is to leverage the fact that in particle physics, say you have the freedom to boost to any frame that you choose. And it's particularly convenient to boost to a frame in which the sum of the momenta, particles 1 and 3, vanish. And you do this for 2 important mathematical reasons, okay, which are just summarized here. The first reason is that this frame is so-called crossing symmetric. What that means is if you look at what the energies of the particles are in this frame, in terms of these Mandelstam variables, you find that the energy of particle 2 is S minus U, and the energy of particle 4 is U minus S. So the only difference between these 2 contributions is really that you've swapped particles 2 and 4. And you see that in this frame, that's really achieved by simply swapping S and U. And the second mathematical property that they have is that they're analytic functions of S and U. So although there's square roots here of M and T, there's no square roots of S or U. So it's really, in terms of the energy S, these amplitudes are analytic functions. Good. Now, what that lets you do is tidy up this causal dispersion relation quite a bit, because now the only difference between these two things are whether there was an S or a U in this denominator. But ultimately, what you've done is factor out some imaginary part of some amplitude. And it's the same function that appears in both contributions. And the second step is to do a second boost, right? And so you use one boost to justify this simplification, and then you do a second boost. If the theory is invariant under boosts, then you're allowed to do as many boosts as you like. It shouldn't really change the physical amplitude. So you do another boost to the center of mass frame, because then you know in the center of mass frame that these imaginary parts that are appearing under these integrals, they're all positive. Okay, you have this unitarity condition from the first half of the talk. And so after having done these two boosts, you arrive at the relation that each of these EFT coefficients, okay, if you were to write them in terms of the underlying UV physics, causality guarantees that it's an integral over some positive measure, and unitarity tells you that the rest of the integrand has to be positive. Good. Fantastic. Now, I haven't mentioned locality in this kind of heuristic motivation for the positivity bounds. I've just said causality and unitarity. So for the purists in the room, let me make the final comment that locality is needed as this extra ingredient, because these integrals that I'm kind of casually manipulating here, they don't always converge, right? Because I'm integrating up to arbitrarily high energies, and you can encounter divergences that require renormalization. And what locality tells you is that all of these divergences and all of that renormalization ambiguity, it only affects the term that doesn't have any s's, right? When n is 0. And actually, once you get to the s squared term, the s to the 4 term, etc., all of those integrals do converge. And so you can use causality and unitarity to argue that these c's are positive. So that's why the positivity bounds start at s squared and not sooner. Fantastic. So now, if we want to do this in cosmology and get some constraint on the shapes of non-Gaussianity that you can find in the CMB, then we have to revise these steps, right? You're no longer allowed to just boost to any frame that makes your computation simple. So what we found is that there's another way to parameterize the energies of these incoming and outgoing particles. So what we can do is, instead of working with these energies, omega 2, omega 4, we can just parameterize them in terms of two new variables, gamma and m. Okay, and this parameterization we cooked up so that it has the two nice mathematical properties that you usually enjoy by boosting to the bright frame. It's crossing symmetric. If you swap s and u, it swaps particles 2 and 4. That was needed. And it's also an analytic function of s and u when gamma and m are held fixed. And if you want the physical justification for why you should do this, why you should parameterize the energies in this special way, physically what this is saying is that you should imagine that you are scattering your particles with this special bright kinematics, but then that process is happening inside a box that's moving through your space-time at some fixed velocity. And the fixed velocity is described by some Lorentz gamma factor m and some rest mass big M. Those are just two numbers that are telling you about the velocity of your box as it flies through space-time. And so when you keep gamma and m fixed and vary s, what you're doing is really exploiting the fact that this box is moving at a constant speed, and inside the box you have the crossing symmetry and the analyticity that you need to run these positivity arguments. Excellent. And then the second step would have in particle physics been to boost back to the center of mass frame. We're no longer allowed to do that, but the results from the first half of the talk, right, using the spherical wave expansion, are enough to show that the imaginary parts are all still positive, even though you're no longer allowed to boost to the center of mass frame. And that's how we arrived at this new set of positivity bounds in theories which violate Lorentz boosts. Okay. And they take the same form, only now the amplitude is a function not only of the energy s, but also of these velocities, gamma and m. But each of these coefficients, okay, they're functions of gamma and m, but they're strictly positive. So we now have this infinite tower of bounds that you can apply to your EFT. So let me close by telling you what these bounds mean phenomenologically. So there's three kind of important consequences of these bounds. The first is that they really have a big impact on simple models. Okay, if you imagine, just to gain some intuition, turning on a single interaction in your Lagrangian, something simple like just pi dot to the 4. If you compute that amplitude and you parameterize the energies in this special way and take 2s derivatives, then the positivity bound really tells you that beta 1 has to be strictly positive. Okay, so that's saying that there's no causal, local, and unitary physics which could ever generate just this interaction with the wrong sign. Perhaps more surprising, if you turn on something like a cubic pi dot cubed interaction, right? This interaction is interesting because it doesn't exist in the Lorentz invariant context, because if you had 3 derivatives, then there's no Lorentz invariant way to contract them together. But now we've broken boost, you're allowed to just have 3 time derivatives. And there, the positivity bounds tell you that alpha 1 has to vanish. So there's just no causal, local, and unitary physics which could ever produce just this pi dot cubed. It would have to always produce other stuff, right? Like at least some of this guy, some of the pi dot to the 4. Now, the second thing that these bounds tell you are that if you take the full EFT of inflation, okay, include all the cubic and all the quartic interactions, okay, you get quite a messy amplitude. But then you can apply these positivity bounds and ask, what does it tell you about these coefficients, beta 1, alpha 1, and CS? And you find that the coefficient that controls the trispectrum, the beta 1, it really is bounded in terms of the coefficients that control the bispectrum. So there is some phenomenological bound that tells you if the UV physics is generating a large bispectrum, it must also generate a large trispectrum. And then finally, as in the unitarity case, it would be really nice if there was a way to somehow remove beta 1 from this expression, because that's the one we have the poorest experimental constraints on. And there is a way to do this. Essentially, you take this causal integral over all energies, and you split it up into 2 regions. You split it up into some low energy piece, where you integrate from energy 0 to the scale at which new physics becomes important, some omega NP. And then there's a UV piece, which is from omega NP to infinity, but that UV piece is positive by unitarity. Okay, so you get an improved positivity bound, which now you can show depends only on alpha 1 and CS. Great. So now to sum up, to wrap everything together, what we've achieved is if the underlying UV physics behind inflation has these fundamental properties, if it's unitary, causal, and local, then inevitably these correlations that you produce at the end of inflation have to satisfy these positivity bounds, which are really telling you something about how the bispectrum is bounded in terms of the trispectrum and abound on 2 different bispectrum shapes. And in particular, there's this combination of alpha 1 and CS that appears in the positivity bounds. And if it has the wrong sign, then it's telling you that the only way that you could ever have unitary, causal, and local physics is if the new physics appeared at a sufficiently low energy scale. So what that lets us do is come back to this picture here, right, where unitarity told us that the EFT only resolved subhorizon scales in this box. And then we can ask, when could the new UV physics that completes this theory, when could that be unitary, causal, and local? And we find that in this white region, it could be unitary, causal, and local at any scale. But if you're in this, say, dark purple blob, the only way that this new physics could be unitary, causal, and local is if it becomes important within an order of magnitude of the background. It becomes important at energy scales below 10H. So that's what positivity bounds are really telling you about the EFT of inflation. Perfect. Good. So what we've seen is that to apply amplitude techniques to cosmology requires going beyond the usual assumptions of Lorentz invariants that are made, because the expanding space-time background really breaks those symmetries. In particular, we focused on scattering in some subhorizon box where we can ignore the breaking of time translations, but account for the breaking of boosts. And we found that when you break boosts, the EFT can have different cutoffs in time and in space, but we developed the machinery that you would need to identify where those cutoffs are in terms of the EFT parameters. And in particular, if you apply them to Planck's constraints on non-Gaussianity, you find that there's this red box that you carve out of the parameter space, where there's just, you need some new physics to appear on subhorizon scales for this EFT to be consistent. And then finally, we turned to positivity bounds, which in particle physics are this nice connection between properties of the underlying UV and signs of coefficients in the low energy IR expansion. And we showed that you can use the same approach, the same methodology in situations where you break boosts. And doing so gives you a new set of UV constraints, which can be applied to the non-Gaussianities that we measure in the CMB. Excellent. So thank you all very much for your time and attention, and I'll be happy to take any questions that you have.